All right, welcome to our explainer for Lecture 14. Today, we're diving into a total game changer, the MapReduce paradigm. This is the model that really unlocked large-scale data processing as we know it.
Okay, so here's our game plan. We'll start with the huge problem that needed solving, then we'll get into the new philosophy that changed everything. After that, we'll break down how the model actually works, see how it's designed to handle constant failure, and finally, talk about what performance really means in the world of MapReduce. So let's set the stage. We need to go back to the early 2000s, because a massive problem was brewing, and it was all about data. Look, by this point, we had incredible systems like GFS and Bigtable, so we'd figured out how to store just an insane amount of data, petabytes of it. But storing it is one thing. Actually doing anything useful with it, that was a whole other monster. We were basically drowning in information from things like web indexes and server logs, and the old ways of doing things were completely breaking down.
And here was the fundamental issue, right? The old school approach was to haul these colossal datasets across the network to some big central supercomputer. But when you're talking about petabytes of data, the network itself just chokes. It becomes a massive bottleneck. It's like trying to drink an ocean through a coffee stirrer. It just wasn't going to work. Something had to change.
So that crisis, that massive bottleneck, it forced a radical new way of thinking. It led to a philosophy that completely flipped the script on how distributed computation was done.
And the idea was so simple, it was absolutely brilliant. Instead of creating a huge traffic jam by trying to move a mountain of data to your code, why not move your lightweight code to the data? Your little program just travels across the cluster, visiting the machines where the data already lives. So much more efficient.
And the whole system was designed with some key goals in mind. First, process just enormous amounts of data. Do it using thousands of cheap, off-the-shelf computers that you know are going to fail. But, and this is the big one, hide all that messy, complex stuff from the programmer. Let them focus on their logic, not on network protocols and failure detection.
Okay, so that's the big idea, the philosophy. Now let's peel back the layers and see how the MapReduce model actually gets the job done. This gives you that 30,000-foot view of the whole operation. It all kicks off with a user program that talks to a central master. You can think of the master as the conductor of an orchestra, coordinating the work across a whole fleet of worker nodes. Let's break this dance down, step by step. First up is the map phase. This is basically the divide and conquer step. The framework takes your giant input file, chops it into thousands of smaller, manageable chunks, and hands one chunk to each worker. All these workers then run your map function on their little piece of data all at the same time in parallel. Now, for the magic, the shuffle phase. This is the secret sauce that the framework handles for you automatically. It's an incredibly complex dance of sorting and sending data across the network. The goal is simple. Take all the intermediate results from the mappers and make sure that all the values with the same key end up on the exact same worker, ready for the next step. And that next step is the reduce phase. After the shuffle has perfectly organized everything, each reducer gets a unique key and the list of all the values that go with it. It then runs your reduce function to do some kind of summary, maybe counting all the values or averaging them to produce the final output. This is where you bring it all home. So putting it all together, you get this beautiful orchestrated flow. The user program kicks things off, the master acts as the director, the map workers chew on their local data, the shuffle phase does its magical sorting, and finally, the reduce workers produce the final answer. It's like a highly efficient assembly line for data processing. But hang on, this entire thing runs on thousands of cheap computers. And what do cheap computers do? They fail a lot. So how on earth does a job that runs for hours or even days actually manage to finish? I mean, this is the critical question, right? If one machine crashing can bring the whole multi-hour job down with it, then this entire model is basically useless in the real world. The way MapReduce handles this is just beautifully simple. The master is constantly pinging every worker, saying, "Hey, you still there?" If a worker doesn't answer back, the master doesn't try to fix it. It just declares it dead. Then it takes all the tasks that were assigned to that worker, even tasks that had already completed, and just puts them back in the pool to be rescheduled on another healthy machine. The job just keeps chugging along. So you see, this idea of fault tolerance is baked right into the system's DNA. Tasks are automatically retried, data is written to a reliable replicated file system like GFS underneath. The The core philosophy is to just assume failure will happen and handle it gracefully without bothering the user. Okay, let's switch gears and talk about performance. This is really important because the main benefit of MapReduce might not be what you think it is. It's not really about speed. And this is a super important point. If you take a MapReduce program and run it on a single computer, it's almost guaranteed to be slower than a normal traditional program. Its power doesn't come from raw single-threaded speed. It comes from its ability to go massively parallel. The real advantage here is all about scale and throughput. It's the ability to take on a dataset that is way too big for any single server to handle and get an answer in a reasonable amount of time by simply throwing thousands of cheap machines at the problem. It lets you solve problems that were otherwise impossible.
And this just puts the scale into perspective. A petabyte is 1,000 terabytes. Sorting that much data used to be a famous, nearly impossible benchmark challenge. MapReduce turned it into a routine task that could be done in just a few hours. So if there's one thing to take away, it's this. MapReduce isn't just a couple of functions. It's a complete framework, an abstraction that truly democratized big data. It made the immense power of cluster computing accessible to any developer, not just distributed systems experts.
And that really leaves you with a powerful thought, doesn't it? By hiding all that mind-bending complexity, MapReduce allowed a whole generation of engineers and analysts to stop worrying about hardware failures and start asking bigger, bolder questions of their data. It really paved the way for the data-driven world we live in today.